Okay, so first of all, let me thank you, Cristina, Francesco, and Olga, for the kind invitation. It's always very nice to be at TPI and in Florence. Um, so, um, so when my idea today was to give a broad overview of this topic of neutrinos from dark matter accumulated in celestial bodies. And when I started thinking about what to talk about today, I thought it was going to be too short, not too much to say without getting into tedious details. And then when it turned out to be completely the opposite, actually, there is actually I started putting things in the talk, and I have a huge amount of material, which is far too much for half an hour. So probably will flash over many things, but at least they are. It is on the slides. I'll talk about whatever I have time for. So what I'll try to do is to tell you a bit about this topic, present you some scenarios that would produce some kind of neutrino signal from dark matter accumulated in celestial bodies. I'll tell you a bit what are some factors which enter in that would increase or decrease the signal, which are relevant for the signal of neutrinos. And then, time permitting, I'll go at the end about an assumption that has been made lately in some papers, which at least in the being optimistic is very challenging. So, but that will come at the end. So there are many. Oh, this is not working. Doesn't matter. Nothing works. Yeah, no, it does. Okay, so there are many connections between neutrinos and dark matter, and we have had several talks in this workshop on that. Of course, we can try to detect neutrinos with neutrino detectors and dark matter with dark matter detectors, but that it's kind of boring at this point. But of course, we can detect dark matter indirectly via neutrino detection in neutrino detectors, and we can detect dark matter with neutrino detectors via dark matter interactions in the neutrino detector. We have had some talk in this conference about this, but actually in this talk, it will be about this, basically detecting dark matter, or saying something about dark matter, detecting neutrinos in neutrino detectors. But also, we can also search study neutrinos with dark matter detectors, and we've also had some talk on that. But there are more connections. Neutrinos could be dark matter candidates, or neutrinos, dark matter could be at the heart of the neutrino mass mechanism. And there could be neutrino dark matter interactions that could be searched for instance, neutrino detectors that could affect astrophysical and cosmological observables, like, for instance, suppressing the matter particle spectrum. So there are many connections between dark matter and neutrinos, and I'll focus on the rest of the talk. But let me say a few more words about these neutrino dark matter connections and interactions. So the way that there are basically three types of signal in which we can search for this or interactions. One way is to search for a new signal. So dark matter produces a new signal in the form of neutrinos, which is, as I said, will be the topic of this talk. But dark matter and neutrino interactions could produce features on known, for instance, neutrino spectra, suppressing, producing some dips or something on high energy neutrinos, for instance, astrophysical neutrinos. Or neutrino dark matter interactions could produce, for instance, matter power spectrum and suppress matter power spectrum at smaller scales that can be searched for in cosmological and astrophysical observables. Again, insisting, I'm going to talk about this part, but these are basically the three broad ways in which neutrino dark matter connections would show up in different observables. And we have listened in many talks about all these different or many of these sources, natural sources and man-made sources of neutrinos. Now, I will not talk about any of this, and today I will be talking exotic, which are neutrinos one way or another produced by dark matter. And we have seen this plot, which is very nice by Georg and company, and which is all the fluxes, natural fluxes of neutrinos across the energies. And for this talk, I will not be talking about any of these fluxes, and actually they will be basically I'm going to discuss, which is basically neutrino signals from dark matter. Okay, so we concentrate on new signals. So how could dark matter produce a new signal in the form of neutrinos? So there are basically two grand classes in which dark matter would produce a neutrino signal. One way is dark matter could annihilate or decay in galactic halos or subhalos or whatever, and we can search for that neutrino flux from, for instance, the center of the galaxy. And another way is to search for annihilations of dark matter captured in objects like the sun or the earth or some other celestial objects. And that is what I will be discussing about these kind of signals, how we can search for and what type of scenarios would produce a neutrino signal from dark matter accumulation in celestial objects. Okay, so actually the accumulation of dark matter in celestial objects has many other implications, and that would be a different topic for a broader talk. But I just want to mention that this accumulation of dark matter could have other implications. For instance, it could modify the energy transfer in celestial objects. And actually, this was the original proposal of this accumulation of celestial bodies, in particular in the sun, in the 80s, actually in the late 70s. It was proposed to solve the solar neutrino problem. You modify the energy transfer in the sun, you modify the temperature profile of the sun, you modify the solar neutrino fluxes, and in principle, you could expect to get an agreement with what was the so-called solar neutrino problem. But this dark matter could annihilate if it has accumulated in the sun, for instance, or in any other object. It could annihilate or could scatter with the nuclei of the object and can hit the celestial bodies in a similar manner. I could modify the evolution of a star or any other object. And I'm just quoting here the earlier paper, but there are the literature on these topics is quite vast. And then, of course, one can search for annihilation of dark matter accumulated in these bodies, which I will devote the rest of the talk on this little part here. And in some extreme scenarios, in some extreme under some extreme conditions, one can even, dark matter accumulated in celestial body could even collapse and form a black hole and eat up the whole system. And there are works on that. But that is under kind of some extreme scenarios. Actually, I will not discuss that. I think I have a point where there is a kind of a funny way to look for this kind of black hole formation inside, for instance, the Earth or the Sun. But I'll say something later on. Okay, so I'm going to concentrate on this. And as I said, thinking about this was like, probably you've heard this in many conferences, like when people talk about you hear talk about super K or ice cube or Antares, whatever, like limits on dark matter annihilation from the sun, and then you have a plot on that. That's it. That is the end of the story. That was what I thought it was going to be like that. That's it. No, but there are many more scenarios than the vanilla scenario, and I will tell you a bit. So how does it work? So we have dark matter in our halo, and dark matter has a velocity distribution, and those dark matter particles can eventually collide with the nuclei or electrons for instance, in the sun or any other object. Whenever I say sun, just take it as an example. I'm talking about any celestial object, and those interactions of dark matter particles with the celestial body could bring the dark matter particles to velocities which are below the escape velocity of the system, so that they get gravitationally bound. And after further scatterings, they could get trapped within the system, and then finally thermalize within the system, and then accumulate. And if those particles can annihilate, they could annihilate and produce something. And that something could be, for instance, standard model particles. If dark matter annihilates into standard model particles, like the usual dark matter annihilation to BB bar or tau pairs or W bosons or neutrino pairs, whatever. It turns out that, for instance, if we are thinking about an object like the sun or the earth, if dark matter annihilates into standard model particles, we can search for neutrinos. But not only we can search for neutrinos, is that we can only search for neutrinos, because any other standard model particles that is produced inside these objects will get trapped within and it will not escape. So basically, the only products that will escape from these objects after the dark matter annihilates inside are neutrinos. This is, yeah, exactly is what I was going to say. There are scenarios in which that you can avoid that, and we'll comment on that. But the vanilla scenarios, which you have dark matter annihilation to standard particles, only neutrinos. You need something like a long-lived mediator that exits the object. And I'll comment on that scenario. Okay, so we have these dark matter particles floating around and hitting the nuclei of the targets. And basically, one can study what is the evolution of the number of particles accumulated in these objects by a simple evolution equation, which is well known since the 80s. This is it depends on the capture rate, the annihilation rate of these particles once accumulated, and something which is called evaporation rate, which I will come to talk a bit more at the end of the talk. Basically, the equilibration of all these rates is what sets what is the number of particles accumulated in these objects. And this equation has an analytical solution. Basically, if equilibrium between capture and annihilation is reached, basically the number of particles reaches a steady state, so basically a saturation point where you have a maximum number of particles that gets accumulated. From there on, you can compute what would be the rate of dark matter annihilations given, for instance, whatever annihilation cross-section dark matter has. Okay. Okay, so and what are the main ingredients in the calculation? The main ingredients we have is basically what is the dark matter velocity distribution, the dark matter particles velocity distribution, what are the dark matter nuclei or electron target particles scattering cross sections, what are the properties of the capturing celestial body, what are the properties of the sun, what is the size, what is the radius, what is the mass, what is the temperature profile, that sets all these previous rates that I mentioned before, capture, annihilation, and evaporation, and also the distribution, the velocity distribution of the target, which has to do with the temperature in the body. This is especially relevant for when one wants to compute evaporation. Okay, so I won't get into all the details, but basically the capture rate, when one wants to compute the capture rate, is basically you have to compute what is the flux, which is basically given by this, the flux of dark matter particles going through the celestial body. What is the probability those particles interact with the target particles of the object, and then what is the probability that after those particles have interacted, the velocity, the final velocity of those particles of the dark matter particles is below the escape velocity. That is basically all that enters here. That is all what all these equations say, and that is what one has to take into account. So actually, the calculation of the capture rate when one considers dark matter nuclear interaction is relatively simple. Can be long, but straightforward. And actually, one can take the zero temperature approximation. That is what makes it simple, because the thermal motion of nuclei is not relevant and just produces some 5–10% corrections on the actual. Sorry? Accretion of what? Well, it's the same. Capture rate is the accretion rate. But what do you call accretion here? Because for me, yeah, but oh yeah, definitely, yeah. So in this limit, one can do a calculation. Actually, you can get a completely analytical result, and this is known, I mean, since the 1987 by Gould. And you get the capture rate in the weak cross-section limit when the mean free path is long, and it might look kind of weird or complicated equation, but it's actually very simple. This is just the flux of particles. This has to do with what is the probability of these dark matter particles to interact in the object. This is basically the probability of these particles once they have been captured gravitationally to get to a velocity below the escape velocity, and this is just a gravitational focusing factor. Actually, in the case of very large cross-section, when the probability of interacting is very large, but not only the probability of interacting is very large, but the probability of capturing is very large, one gets the actual geometric limit, which is the physical limit, which is basically telling you this is the capture, this is the surface of the cross-section, the physical cross-section of the object. This is just the flux of particles going through the object, and this is just the gravitational focusing factor. due to the gravitational potential of the object. And the actual limit, the maximal limit that sets the maximum amount of dark matter particles that can get captured. And if dark matter gets accumulated and dark matter annihilates, basically one needs to compute what is the number of dark matter particles that accumulate at a given time, and one can compute what is the rate of these annihilations, which is just given by the annihilation rate times the square of the number of particles. We need two particles to annihilate. And in the case there is equilibrium between capture and annihilation, and evaporation is not important, basically this rate is just half the capture rate. And so the flux, the final neutrino flux at our detector will be the capture rate divided by the distance squared. Of course, when one does a proper analysis, one has to take into account what is the neutrino spectra inside the celestial body, and one has to propagate those neutrinos out of the celestial body up to the Earth. But those are some details you have to take into account. But the general number, basically, that the normalization of this flux is given by the capture rate divided by the distance of the object squared. Okay, so just some consideration before I move on. So, as I said, that this is the flux goes with this, and basically the neutrino flux from dark matter annihilations in any object would grow if the dark matter velocity in the halo is low, because that favors capture. If the dark matter density is high, we have more dark matter particles, then the neutrino flux would also grow. If the escape velocity of the object is large, that also favors the fact that dark matter particles, after interacting, would go below escape velocity, below the escape velocity of the object. And that is the same to say, and I'll show you that later, that the size of the celestial object if the size of the celestial object is large, that also favors capture, because escape velocity scales with the size of the object. Also, if the cross-section is large, there is a higher probability to interact. So that also increases the flux of neutrinos. And also, if dark matter mass is similar to the target mass, then basically the energy transfer in a collision between dark matter particles and target particles is maximal. So that also increases the chances. I'll comment on that. This is one of the scenarios. And some other comments. So let's do some numbers here, just to give you a flavor of where we are. So let's suppose that we have maximal capture. This is a very rough number, so don't use this in any analysis. So let's suppose that we have maximal capture, and we want to compute what would be the flux of neutrinos from the Earth compared to that of the Sun. And basically, that is the ratio of the distance from the Earth to the Sun to the radius of the Earth. And so that turns out to be like a very large number. So the flux of neutrinos from the Earth would be much larger in the case of maximal capture. So that we are in the limit of very large cross sections. But what happens otherwise, which is usually the most common situation? The flux of the neutrinos from the Earth, the ratio of the flux of the neutrinos from the Earth to the flux of neutrinos from the Sun is much smaller than 1. So actually, there are many more neutrinos expected from dark matter annihilations in the Sun than from the Earth, if the cross section is not extremely large. And this just depends. You see, this is escape velocity. This is mass and radius of the Earth and the Sun. This is mass of the Sun. This is the dark matter mass, and these are the distances. So these are very, very simple numbers. One can do it in 1 minute, and you get order of magnitude reasonable results with this. But one can also wonder, would the flux for any other, for instance, planet in the solar system be comparable to what we expect here? Actually, if one does the same exercise as here, comparing the flux from the Earth to the Sun, instead of putting the Earth, let's put Jupiter. What is the flux of Jupiter at the surface of Jupiter compared to the flux of the Sun at the Earth? That is comparable, because Jupiter is a better capturer than the Earth. So instead of being 10 to the minus 3, it's order 1. Actually, it's even larger than 1. The problem is that we don't have a detector at the surface of the Earth. So we have to penalize the distance of the Earth compared to the distance to Jupiter to the radius of the Earth, and that adds a 10 to the 8 factor, which penalizes the fact that we don't expect many neutrinos from Jupiter. So in general, we don't expect that any other planet can compete with the Sun or even with the Earth when at producing neutrinos from dark matter accumulation. But one can also wonder, could the neutrino flux from the integrated flux of all stars in our galaxy be comparable to the flux of the sun? And one can do very simple exercise. The closest star to us beyond the sun is Proxima Centauri, which is about 4 light years. One can do this exercise of just assuming that all stars produce a similar flux, which is not a crazy assumption. One just does this, so the ratio of these distances square is like 8 times 10 to the 10. So basically, we need all stars in our Milky Way galaxy within Proxima Centauri distance. Basically, the answer is no. The sun flux of neutrinos is larger than the flux produced by all stars in our galaxy. Not only all stars in our galaxy, all objects in our galaxy. Okay. It does. It depends on the cross section. It depends on the mass of the system. Well, it depends on the number of particles. No, but it's not. Is what matters is what is the escape velocity. Actually, neutron stars are very good capturer because they are very compact, so the escape velocity is very large. So basically, any interaction in a neutron star would bring the particle below the escape velocity of the neutron star. That doesn't happen with the Earth. Actually, the sun is better captured because the escape velocity of the sun is larger. So it's the escape velocity what matters. Yeah. Despite the generation, yeah. But despite that, it's very, very little energy losses now. So it's what I said before. Objects with a larger escape velocity are better capturers. And that scales with the size of the system. I'll show you a plot of that later. So this is the usual plot, which I thought I would finish my talk with, and that would be like 5 minutes, and that's it. This is the plot. You hear limits from Super K, IceCube, Antares, Baxan, Baikal, KM3 on the cross section, this is the scattering cross section as a function of the mass of the WIMP, and you see this is for spin independent. It reaches levels of 10 to the minus 7 picobarns or so at a few hundred GeV. Still, for spin independent, direct detection experiments get a better band on the scattering cross section. These searches do a little bit better in the case of spin dependent, which are all these color bands. The different colors represent different annihilation channels. It's into tau pairs or into BB bar. The flat neutrino flags are different, so you get different bounds. Usually, you get better bounds for annihilation channels that produce a harder neutrino spectrum because higher energies cross sections are larger. Atmospheric neutrino flux is lower. But still, at low masses, this is the direct detection limits. This is a bit a factor of a few off. Turns out that this is not so anymore. There is a recent IceCube deep core analysis using 7 years that I think this is the pico bound, which is this one. And these are the deep core bounds for some channel. Already, these kind of searches, in the case of spin-dependent cross sections, are more constraining that direct searches. I'll come to that. The short answer for that is no, but I'll come to that. There are many other analyses searching for these kind of signals with different type of detectors. I know future prospect for hyper-K or so. I won't get into that. Of course, one can do the same exercise for and set limits with fluxes from the Earth. And the limits, as I said before, are slightly weaker because the flux expected from the Earth in the let's say in the not very strongly interacting regime, which is for this cross section, we're in that regime. So they are slightly weaker. And you see like what happens with the sun, all the curves were very smooth. Here, in this case, you see all these peaks. These peaks is precisely because the Earth is not a very good capture, and the escape velocity of the Earth is much smaller than the average velocity of dark matter particles in our halo. This is where the energy transfer gets maximized. This is basically, these peaks represent where there is between the dark matter particle and the scattered mass. So this is iron, carbon, oxygen. So this is where the peaks are, where the air transfer is maximal, and then you can actually produce that. This doesn't affect the case of the sun, because in the case of the sun, the escape velocity is larger than the typical velocity of the dark matter particles in the halo, so you don't get an enhancement of this sort. And in the case of the Earth, unlike what happens with the sun, because in the sun you can dark matter can interact with hydrogen, can interact with other type of nuclei. In the Earth, we have very little hydrogen, or very little amount of elements which have unpaired nucleons that can prove a spin-dependent cross-section. So basically, when you see a limits from a spin-dependent from dark matter annihilations from the Earth, the limits are on a spin-independent cross-section, not on spin-dependent. You can do it, but the fraction of elements is below the percent at the Earth. 10 minutes. Okay. So you have the annihilation into different channels, but you have to capture it. The capture goes through the scattering. You can capture via spin-dependent or spin-independent interactions. Okay. Yeah, this is already in the equilibrium case. So it's basically the annihilation is basically half the capture, yeah, and the capture depends linearly on the scattering cross section. Of course, not in equilibrium, there is a dependence on the annihilation cross section, but actually the annihilation cross section typical from thermal dark matter, which is 3 times 10 to the minus 26 centimeter cube per second. If you want to produce that thermally, usually for the Earth or for the sun, these are all equilibrated for these cross sections. So the final dependence, the final flux of neutrinos doesn't depend on the annihilation cross-section. This is the scattering cross-section. This is a spin-independent cross-section. Okay, but this is kind of the vanilla. I have 10 minutes and I have spent what I thought it was going to be 5. But one can actually, these are usually the branching ratio, and dark matter can annihilate into different channels. It can annihilate in top pairs. It can annihilate W bosons. It can annihilate into heavy quarks. And this is all the bounds that I showed you before are for that. But what if dark matter annihilates into light quarks, or what if dark matter annihilates into muons? You never see those plots in this kind of analysis on those plots. So the reason for that is if dark matter annihilates into light quarks, it produces pions. If the dark matter annihilates into muons, it produces muons, of course. And but those in a system like the Earth or the Sun, which is quite dense in the interior, basically get completely stopped before decaying. So what happens is that the flux of neutrinos that is produced in these cases is a flux coming from pion or muon decay at rest. So this is a flux of tens of MeV neutrinos. So what about that? So that is actually what we did like 12 years ago. Actually, these were 2 papers, and luckily we coordinated because we learned about each other working on this. And I coordinated with Karsten, Jenny, and John, and we submitted the 2 papers on the very same day. Luckily, we agreed on the results. But one can search for this MeV neutrinos, and we've had some talk on the DSMB. With super K, those are tens of MeV neutrinos. These are pion and muon decay. One can search for those neutrinos, and one can use the super K data. This is what we did in our paper, and set bounds on the spin-independent cross-section and the spin-dependent cross-section. The bounds are not that fantastic. These are direct searches, and actually these are the bounds as in the paper. So 12 years ago, the actual bounds these days on direct detection are much better. So only maybe a spin-dependent at very low cross-section, this can get somehow competitive. Actually, as a follow-up, Karsten did another possibility, which is what about neutrinos from kaon decay at rest, which produce neutrinos with much higher energies, 236 MeV. This cross-section is always nucleons. This is dark matter nucleon cross-section. And then the dark matter annihilates, produces in the different channels, and in this case produces pions and muons that decay at rest, and the signal is pion muon decay, the neutrinos from pion muon decay. And in this case, is in the case kaon decays, so produce line neutrinos with 236 MeV, which have higher energies and actually can get bounds which are 1 or 2 orders of magnitude better. Anyway, so we are getting to the juicy thing when we have 5 minutes or so. So we have what about strongly interacting dark matter? Actually, we go to the thick regime. very high interaction probability. So the probability for dark matter to interact is very high. That doesn't actually mean that the probability of being captured is very large. So if the dark matter mass is very large, the energy transfer is very low. Actually, this case with the ratio of the mass of the nucleon to the mass of the dark matter. So one should be very deep into the thick regime actually to have a very efficient energy. But very light dark matter happens the same. Yeah, if it is comparable, yeah. But one can test a very heavy dark matter, and actually there was a work using IC22, very preliminary. I haven't seen an update on this on very large cross sections of very heavy dark matter. And recently there have been a couple of papers by Maxim Pospelov and collaborators, where actually they considered this. The previous paper was dark matter, strong interacting dark matter in the sun. This is in the Earth. Actually, one can search for dark matter annihilation in the Earth with neutrinos from pi indices and from neutrinos, or for very light dark matter, like few GeV, dark matter, the distribution of dark matter capture inside the Earth would be very homogeneous. Not usually dark matter, when it gets captured, it to the center. But the lighter the dark matter is, the more spread is the distribution. So for very light dark matter in the few GeV range, basically dark matter would be covering the entire Earth. And one actually can look for dark matter annihilation inside the detector, because the density of dark matter inside the detector could be larger than the usual local dark matter density in our local neighborhood. So there could be limits, and actually one can test that this kind of strongly interactive dark matter is just as, if it is much lighter, it would evaporate. So one can actually test that only a tiny fraction of this, the dark matter has this strongly interactive behavior, and they show that you can prove fractions of at the level of 10 to the minus 10 with this kind of searches. Okay, but so far I've only talked about dark matter nuclear interactions. What about dark matter interaction with electrons? Actually, in this case, thermal motion is crucial because electrons are much lighter, so they move faster. And this was proposed in this paper by Joachim et al. Joachim Kopp et al. And actually, we did a detailed analysis with Raghuveer Garani, where we saw actually that the thermal effects on the capture rate could be orders of magnitude. And one can test this with leptophilic scenarios. Actually, it turns out that even in leptophilic scenarios, you always have a loop level. And dark matter nuclear interactions are more effective at capturing. And it turns out that in most cases, we are working on that. Actually, we are working on we are doing this for many years already, so we never finish. But it turns out that in many scenarios, basically dark matter nuclear interactions at loop level dominate the capture process over dark matter electron interactions at the tree level. But anyway, this is, I'll go fast. So what about self-interactions? In self-interaction, have been proposed to solve many different astrophysical cosmological problems. And actually, there was a discussion by Andrew Sender 15 years ago, how this could help or how this would change the problem of dark matter capture. And actually, it turns out that self-interactions can enhance capture rate. You can have a very tiny dark matter nucleon interaction, but enough to produce a seed of dark matter particles captured in the object, and a huge dark matter interaction that would enhance the capture rate at a significant level. Actually, the level that can be proved of the self-scattering cross-section of dark matter particles is at the level of what is needed for to solve these astrophysical questions. But there are more questions here. There are not only self-capture, there is self-ejection, self-evaporation. I don't have time for that, so I will skip it. What about secluded dark matter? We have which dark matter annihilation to a mediator that escapes the object, can decay outside the object or just farther out of the object. And if the decay is outside the object, one can also search not only for neutrinos, but for any positrons or photons or whatever. And basically, what happens for neutrinos is that if neutrinos, then the high energy neutrinos would be absorbed in the system, so you have a larger flux of high energy neutrinos. Okay. This is for the Earth, but I don't have time, so I will not get. So one can search also for secluded dark matter from other objects like neutron stars or brown dwarfs. What about inelastic dark matter? In the case dark matter is composed of two, we have the dark sector has two components with very degenerated mass, which are mass splitting, which is in the order of keV. In that case, actually, it was so many years ago that this is a way to evade direct searches limits. So limits from direct detection can be relaxed in that way, because you need energy to be supplied to produce the heavier state. Basically, there is no energy to produce the recoil nuclei. Actually, you can completely avoid those limits. This would also, of course, reduce the capture rate, but it doesn't suppress it. So actually, there is a range of parameters or values of this mass splitting at the level of 50 kV or something like that, in which you can completely evade direct detection limits, but they still have a significant bound from neutrinos from the sun. Actually, there's a very recent proposal of months ago, and where they show that you can search for this inelastic dark matter annihilating outside neutron stars, where the splitting is in the order of 100 MeV, because basically the dark matter wouldn't have time to thermalize inside the neutron star. One can search for the neutrinos produced from annihilation outside the neutron star. Anyway, so there are many other possibilities. I don't have time to discuss all of those, but we mentioned before about the black holes. One can produce if dark matter gets accumulated under some circumstances, could produce a black hole inside the Earth or a black hole inside the sun, and tiny enough so that it evaporates. And in that evaporation, we heard yesterday from Hubert, it produces a flux of neutrinos, and one can search for those neutrinos coming from a dark matter accumulating in the sun, producing a black hole, and black hole evaporating and producing a flux of neutrinos. But there are many other ways to do that. But let me just finish to say this kind of controversial assumptions in the late literature. So the question is, can dark matter particles have any mass and be actually efficiently captured in objects? The short answer is no. So there is a limit, there is a mass, which is the so-called evaporation mass. So if dark matter particles are very light, the chances for these particles to scatter a nucleon or nuclei and acquire a velocity larger than the escape velocities are larger, the lower the mass is. So this is what is called dark matter evaporation in celestial objects. So what is that minimum mass for evaporation not to be efficient, for evaporation not to be efficient? And given that the evaporation rate is an exponential, has an exponential dependent on the mass, the actual definition is not very important. One can do this definition has been done. This definition has been made since the 80s, so that the evaporation rate times the equilibration time is of the order of 1. And you change this by 1 order of magnitude, you get basically the same result. The equilibrium time is when capture and annihilation equilibrate, and this is basically the square, I don't have it here, is the square root, 1 over the square root of the capture time the annihilation. This is basically when the number of dark matter particles stays the same. And okay, so actually the short answer, if you want to compute the evaporation mass for any object in the entire universe, any object which is in hydrostatic equilibrium in the entire universe, this is what you need to do. It's a very simple calculation. This is just the escape energy of dark matter particles in the center of the object divided by the temperature of dark matter particle is very close to the core temperature of the object, equal to 30, which is along the tail of the distribution. You do this, you get the correct answer within 20% for any object in the universe. Okay, but let's, well, I won't get some details, but let me show you some. So actually, you can compute the evaporation with all the details. You can do the full calculation of the evaporation mass for the sun. You get E over T 29. For the Earth, you get E over T 34. Everything within 10, 20%. And you get the actual masses. You put the right numbers here, which is just, you only need to know what is the mass of the object, the radius of the object, and the core temperature of the object. That's it. You get the number. So, what is what? This is the escape energy of dark matter particles in the core of the object. Mass of the dark matter times the escape velocity is correct. Yeah. So this is why you need, there is a little dependence on the profile because it's the escape velocity, but it's, this is a lower limit. I mean, the dark matter cannot get captured if the mass is smaller than this. Yeah. So, and then one can wonder, so what is the evaporation mass, not in the sun or the earth? What is the evaporation mass in any object? So one can do this, one can get the radius of, as a function of the mass. We did this for 12 orders of magnitude in mass from dwarf planets to giant stars. The same for the core temperature. You can do this, and you see the escape velocity as a function of the mass. As I mentioned before, the escape velocity grows with the size of the object, and then you can show this. And one can compute the acceleration time. But anyway, so I want to get to this plot, which is what is the evaporation mass for a particular value of the cross-section, which is the so-called geometric cross-section for the local density. In any case, the dependence on this parameter is logarithmic. So this is very, very stable. And you see that this is the evaporation mass as a function of the mass of the object from 10 to the minus 10 solar masses to 100 solar masses. And you see that the minimum mass in the entire range is for the brown dwarfs or the more giant Jupiters, which is about 0.7 GeV. And as I said, this is very stable when varying many other parameters. We computed this for 10 orders of magnitude in cross-section as a function of the mass, and the variation is within a factor of 2, something like that. 10 orders of magnitude in the cross-section just varies within a factor of 2 the evaporation mass. So yeah, a few hundred MeV is the lowest you can get. We did that for neutron stars or white dwarfs. Of course, these are much better capturers, so the evaporation mass is lower. MeV for white dwarfs, KeV for neutron stars. But this is known for almost 40 years or 35 years. So what is all this about computing this? So the point is that we wanted to do a systematic study in the first place, but it turned out that at the time we're doing this, there were a number of papers that appeared claiming that dark matter evaporation masses in the MeV range, that it can capture dark matter down to masses in the MeV range. Lately, I mean, in the last year or so, there have been even claims that the evaporation can be completely forgotten. So you can forget about evaporation, and there's no evaporation, which is a very model-dependent statement. And so basically, that is wrong. So there are many papers with interesting ideas, but they are going claiming to prove ranges of masses down to MeV ranges. There are many papers of different type of ideas you see going to masses 10 to the minus 3 GeV. And that implies that you need evaporation not to be effective at all. Actually, there are papers where you go all the way. And the point is that how can this be possible? At first, it was a mistake in the calculation. Then there were other things. So actually, if you do the proper thing, instead of covering, you see brown dwarf, they were claiming to cover up to here. Actually, you're covering all this way. So basically, you are left with no coverage. I was lazy enough to put it in all those, just to give an idea what is the actual values that these kind of searches could cover. But so this is just my final slide. So is there a way out? So can you just play with the location of the object or the annihilation cross-section? I said all these dependencies for the evaporation mass are logarithmic. So in order to change a factor of 2 the dark matter mass, the evaporation mass, you need to change like 10 to the 13, for instance, the density of the dark matter. So complicated. So spin dependent. Yeah, this changes just at the level of 20 or less %. What about adding self-scatterings? What about if you add self-scattering, does it change the dark matter evaporation mass? It does, but it goes in the other direction. It makes it larger. So what if, I mean, we did a simplified treatment of for instance, the profiles of the different objects. But you can play with all those profiles and you won't get variations larger than 10%. What about uncertainties in the composition? You can play with extreme composition. You can take Earth only hydrogen or a Sun only iron. You will get basically smaller than 10% variation in the evaporation mass. What about uncertainties in the core temperature? These are equilibrium. So the core temperature is very set by the Virial theorem. And then there was last year, there was a proposal that there could be attractive long-range interactions that would add to let's say, they would increase effectively the evaporation, the escape energy. However, for that, and I don't have time to get into the details, this, at the very least, would require extreme fine-tuning. But not only that, they are proving contact dark matter interactions that
that would produce at loop level a field force which is completely excluded. So, I mean, there have been in the last months or papers appearing proving a space, proving MEV dark matter with capture. No, I didn't do it. Yeah, it's attractive force that contributes to gravity and makes this effective. Well, that's a issue. That's one of the issues. But anyway, the claim is that you had a very long range force, attractive long range force that contributes additionally to gravity, so that you prevent dark matter particles from evaporating. That is the logic behind this. The only problem is that it has. I mean, the only problem. The problem is that there are many issues with this setup that you end up into basically regions of the parameter space which are completely. Both. Yeah. I mean, as I said, I cannot get into it. We can discuss, but basically the claim is that you add this force, you prevent the dark matter from evaporating. The problem is that the parameter space, the parameters that you need for this to work are completely excluded. Or very fine-tuned. Anyway,
let him conclude.
Let me conclude. So basically, just wanted to say that dark matter accumulation celestial bodies can be proved with neutrinos in many different ways, and but getting something like masses below some hundreds of MeV would require extreme conditions, or even invoking extreme conditions that is very complicated. Thank you.
Okay, so there have been already questions. There are a few more or comments. If you continue, maybe so let us see if other people have questions or comments. Yeah. Okay.
Yeah, from the experimental point of view, by the way, so far I mostly there is no evidence.
No, everything is compatible with atmospheric neutrinos.
Other comments or questions? You can continue during the coffee break unless it's very urgent. I need a coffee, at least a 10 minutes break, I think we need. Okay.
No, I mean, finite temperature effects are important. But finite temperature effects are important in the computation, but this is all classical. For instance, in the computation, evaporation is critical, because what happens is you have dark matter which is trapped inside the object, and how does evaporation work? The dark matter scatters a nuclei in the sun and goes to a velocity larger than the escape velocity. But in order to do that, it has to get some energy from the nucleus. So you have to take into account the thermal motion of the nucleus. But this is all classical physics. I mean, for all these long-range interactions, thermal effects, thermal masses and all that are critical actually in the computation. But that is not for the generic problem. Thermal effects are important for evaporation, but at the classical level.
Okay, so.
Exactly. I mean, if you put E equals 0, there is no evaporation. There is no energy for the dark matter to gain to escape.
No more comments or questions. So let us thank Sergio again.